In this video, we're going to look at finding an error estimate for the Simpson's rule. That means we want to find an upper bound on the error of approximating a definite integral using Simpson's rule. So let's assume that the fourth derivative, the absolute value of the fourth derivative, is less than or equal to k. That means k is the maximum of the fourth derivative of the function on the interval a to b. Error Simpson's is defined to be the upper bound of the error of applying Simpson's rule to estimate the definite integral a to b f of x dx. So error Simpson's is equal to absolute value, the definite integral a to b f of x dx, minus the Simpson's rule approximation Sn is less than or equal to k times b minus a to the power of 5 all over 180 n to the fourth. So this is a formula we're going to use. We're not going to prove this rule, we just accept it. So the key concept is k is the maximum of the fourth derivative, and we have to find that for a function. And that's the hard part of finding the error estimate for Simpson's rule. All right, so here we have a question. Apply Simpson's rule with n equals 4 to estimate the integral 0 to 1 e to the x squared dx. That's part A of the question. Part B is estimate the upper bound on Simpson's error bound of this approximation. And part C is how large should n be such that the Simpson's rule approximation to the definite integral 0 to 1 e to the x squared dx is accurate to within 0.00001. 4 zeros and a 1, that means I guess that's 1 over 100,000. All right, so let's start with the solution. Our function, the integrand, is e to the x squared. N is 4. That's the number of intervals. Delta x is equal to b minus a over n. That means it's 1 minus 0 divided by 4. That's equal to 0.25. Because a is 0, b is equal to 1. This is a lower limit of integration. This is the upper limit of integration. And delta x is b minus a over n. All right, so we draw our line, and this has all the x values that are equally spaced, and the partition width is 0.25, and we have 4 intervals. So the Simpson's rule approximation formula is applied. Integral from 0 to 1, e to the x squared dx. This is approximately equal to S4. That's equal to delta x, that's 0.25, divided by 3. Times f of 0, evaluate the function at 0, plus 4 times f of 0.25, plus 2 times f of 0.5, plus 4 times f of 0.75, plus f of 1. Now plugging this into the function, we get S4 is equal to 0.25, that's delta x, divided by 3. Now, how do we evaluate f of 0? We know the function f of x is e to the x squared. So plug 0 in for x. That's e to the 0 squared. Plus 4 times e to the 0.25 all squared. Plus 2 times e to the 0.5 all squared. Plus 4 times e to the 0.75 all squared. Plus f of 1 is e to the 1. If we put this into a calculator, we get S4 is equal to approximately 1.46272. So this is the Simpson's rule approximation to the definite integral 0 to 1 e to the x squared dx. The question, of course, is how good is this approximation? And that's what part B of the question is going to look at. So S4, this is our approximation, is 1.46272. All right, let's look at part B. Here we have the Simpson's rule error estimate. We have the formula. Our goal is to find the maximum of the fourth derivative of this function. So the function is e to the x squared. This is the function. We can compute the fourth derivative, although I'm not going to show you the steps for this one, but you should be able to do it by applying product rule and chain rule and power rule from calculus 1. So f fourth of x, if we do the computation and simplify it, it will come out to be 12 plus 48x squared plus 16x to the fourth times e to the x squared. Now we know that x is between 1 and 0. So it's clear that the fourth derivative is an increasing function on the interval 0 to 1. And if it's an increasing function, the maximum is attained at the right endpoint, at x equals 1. So f fourth of x, that's equal to 12 plus 48 x squared plus 16 x to the fourth e to the x squared. This is less than or equal to 12 plus 48. Plug in 1 for x and plug in 1 for x here, and we just get 16 times e to the 1. And this comes out to 76e. This is the maximum of the fourth derivative. This is the value of k. So now if we plug in k is equal to 76e, a is 0, the lower limit of integration, b is equal to 1, and n equals 4. 4 partitions, 4 intervals. So the Ayres-Simpson's is going to be less than or equal to 76e, that's the value of k, times b minus a to the 5, that's 1 minus 0 to the 5, divided by 180 times n to the fourth. N is 4. And if we plug this into a calculator, we will get 0.00448. This is an upper bound on the error of approximation. All right, now part C of the question is asking find n, find the number of partitions, number of intervals, such that the Ayres-Simpson's is less than or equal to 0.4001. That means we want the error to be less than 1 over 100,000. All right, we have the formula, and earlier we found k to be equal to 76e, a is 0, b is 1. Our goal is to solve for n to get this level of accuracy. So let's do that. Ayres-Simpson's is less than or equal to 76e times 1 minus 0 to the power of 5 divided by 180 n to the fourth. We don't know what n is. We have to solve for it. We're going to make this error less than or equal to 0.00004 zeros and a 1. And our goal is to solve for n. All right, so what we're going to do is let's flip both sides so we can get n to the fourth on top. So now we have 180 n to the fourth divided by 76e is larger or equal to 1 over 0.1234 and 1. Now let's multiply by the reciprocal of 76e, divide by 180 on both sides, and 76e, divide by 180, and we're going to get n to the fourth is larger or equal to 100,000 times 76e divided by 180. If we plug that into a calculator, we're going to get n to the fourth larger or equal to 114,771.9. And if you take the fourth root of both sides, we will get n larger or equal to 18.406. Now here's the most important thing is, you have to round it up to the next even integer, because Simpson's rule requires even number of integers. So rounding it up to the next even integer, that means n is equal to 20. If we take 20 intervals, our error will be less than 1 over 100,000. All right, thanks.